Hello everyone. My name is Mehdi Benes. I'm a professor here at the Center for Wireless Communication at the University of Oulu. Very happy to be introducing the first lecture of the new course entitled Strategic Learning in Wireless Networks, Theory and Applications. I'll be giving this course with Dr. Sumodu Samarakon, who is an assistant professor here at the ICON group, and also Dr. Anitel Gabli, postdoc in ICANN group, and also Dr. Shawqi bin Isaid, postdoctoral researcher in ICANN. So the outline of the course is as follows. So we will have essentially four parts. The first part will be about the force motivation and basics of game theory, which is mathematical tools from economics, which has been used for a long time now to model strategic interactions among agents, right? And we'll see how to apply also this theory in certain wireless communication settings. So this week covers 4 hours, so I'll give the first part of this part, and then Sumodu will cover the homework assignment part with the tutorial. Basically, recap of what I'll be presenting first in the theoretical part, and then guide you through tutorial and also our homework possibly to fully understand this part. Then the second part will be about reinforcement learning, and here this will span 2 weeks and a total of roughly 8 hours. And here we will go through again some fundamentals of reinforcement learning and how to apply it, and particularly focusing on one part of reinforcement learning, since this is a very vast topic on its own. And then once this part is over, then we will move to a different yet related framework of distributed machine learning at the edge of the network. And this is a very comprehensive part, which will actually span 3 weeks. And here we will go over a number of algorithms that are typically different in a centralized machine learning setting. Here we're talking about distributed model training over distributed agents, and the goal is to typically train a model in a communication efficient manner. And here we'll be focusing on 2 different aspects of edge AI, namely how to apply essentially edge AI for wireless network, but also how to leverage wireless connectivity to speed up the training of models. And this part will be given by Anis. This part will be covered by Shawqi. And likewise, we will follow the format of first 2 hours, 1 hour and a half lecture, followed by a tutorial, essentially, to clarify any unclear point. And then finally, the projects will be after the exam. And here the idea is to assign you a number of topics, and then we will see, depending on the interest, how many groups will be formed to take this project. Obviously, this project will be about the application of what you have learned here in the theory, which could be also useful for your own research, especially for those working on machine learning and applications in wireless communication. So again, this is roughly the outline, and here, of course, the idea is really to test your capabilities to understand new concepts and how to apply them to your daily problems, not to memorize these techniques, but again, how to leverage this and help you solve your own problems, because most of these problems actually have a lot of things in common in terms of either optimization problem or in terms of just applying a known tool to solving your own particular problem. More administrative issues here. Essentially, all the lectures will be posted on Moodle. I think everyone has received the link, but if you haven't, please contact us. In terms of credits, everyone knows there are 4 mandatory CTS here, which involve the exam, and then for those interested in the 3rd additional credits here, which is optional. Now, in terms of references, I mean, there are a lot of references here, but these are typically the ones we mentioned. So this is a book on game theory and learning for wireless networks, which covers actually the first 2 parts, namely game theory and part of reinforcement learning. And then the part related to Edge AI, I mean, this is just one of the latest paper here, but yeah, you can find it in the proceedings of IEEE, covering basics, fundamentals, and applications of a number of algorithms that you will learn during this course. So just as a disclaimer here, so this course essentially focuses on, of course, the topic of strategic learning in wireless networks, its principles and applications in wireless communication. So here essentially what we are after is trying to understand how distributed agents in a network learn to interact with the environment, learn to estimate their own utilities over time, and then act upon their estimated utility to update this transmission strategies, right? And there are a number of constraints. So one of them, of course, is the fact that the network is dynamics, uncertainty in terms of local information available to every agent, and of course resource constraints when it comes to communication efficiency, storage, memory, and other constraints. And as I said before, this course will also cover one important aspect of machine learning, namely distributed and communication efficient machine learning here, and this is the 3rd and 4th part of this course.
So why are we here? Well, first, I mean, these are just bullet points here, but essentially to revisit basics of game theory, which is an essential ingredient for learning in general, especially when you have competing agents or selfish agents in a given environment. We want to learn how to model agents interactions and formalize a game, and we will see what we mean by that. We want to learn how do agents can self-organize with or without implicit coordination. This could be ideally among, in a totally distributed manner, or using a kind of centralized server that would actually help you via an implicit signal. We want to tackle the problem when the number of agents becomes very large, and here we will see actually there are very nice tools inspired from statistical physics, namely mean field game theory, and how we can actually abstract this complexity and help us solve these intractable problems in an elegant manner. And finally, how to train machine learning models in a communication efficient way, distributed manner. In the bottom line here, you can see actually the big picture in terms of what kind of mathematical tools are useful when one talks about machine learning or AI or learning in general. So of course, learning or machine learning is one such a tool, but also there are other adjacent disciplines which are very important when one wants to talk, for instance, of reinforcement learning. This is essentially related to control theory. Physics also is very important for, and I talked about mean field game theory briefly. Information theory obviously is a very important when you want to characterize or calculate the entropy or model uncertainty. And of course, there are many other tools. And optimization theory, of course, goes without saying. But again, we need a large set of tools to be able to tackle different problems. All right, so let us start with the motivation here, dedicated to basics of game theory. All right. So first, we need to set the scene a little bit. What is happening with the advent of 5G, beyond 5G, or even 6G? So what we can already see is that networks are getting more and more complex, right? Of course, already with the advent of 4G, we could see the development of small cells or picocells in order to increase the coverage and boost capacity. Then, of course, we can also talk about device-to-device communication, licensed versus unlicensed bands, going for high frequency, 30 gigahertz, and even beyond that nowadays within beyond 5G discussion. Caching was a very popular technique in order to offload the backhaul and maximize the quality of experience of users. And then gradually we saw the addition of new verticals and new devices, even for example drones here, which can provide on-the-fly communication as opposed to for example terrestrial base station. And then we also had, of course, new verticals, for example virtual reality, vehicle-to-vehicle communication, and many others, vehicle platooning, and so on and so forth, right? So the bottom line is that networks are getting extremely complex, calling for new optimization techniques to optimize. Now, also in terms of use cases and applications, I mean, you can see here, this is taken from Nokia paper back already in 2016. You can see here, for instance, I mean, if you want to look at the requirements in terms of latency and bandwidth requirements, you can see that actually there's a whole host of different applications ranging from virtual reality, augmented reality, system control, for instance, for remotely controlling a drone, a factory plant, for instance, things, for instance, for sensors, temperatures, and so on and so forth. Home sensors here, these are maybe very low in terms of bandwidth requirement, but latency may be high. And then you have video, of course, for video streaming, 360 degrees, high resolution, which again here requires a lot of bandwidth, but may afford some sort of latency. Anyways, the bottom line here is, in fact, we have a mixed set of requirements. A lot of data is generated at the edge, which we'll later see how it translates in terms of requirements for learning, machine learning model in a distributed manner, right? So now the question is, how do you optimize such networks? Well, typically, if you want to do so, we have 3 degrees of freedom. One, we can use multiple antenna systems, such as multiple input, multiple output, a transmitter and a receiver. We also have spectrum in order to increase the capacity, how much transmission bits one can push per hertz, for instance. And here again, you can exploit licensed, unlicensed, and a mixture thereof. And then, of course, you can deploy more small cells, or heterogeneous networks. This includes, again, small cells, picocells, distributed antenna systems, and other low footprint transmitters. Now, of course, in beyond 5G, we started talking also not only about bandwidth and small cells or base stations and spectrum, but also now increasingly the resources that we need to optimize are data, energy, and compute. And this is essentially how we could capture these two here. This is the typical one. I mean, this was already in 4G and an early 5G evolution: bandwidth, spectral efficiency, density, and then these are the new kind of important resources, maybe even more important than the others, namely the energy. So here, this is the energy of the compute, but of course could be end-to-end energy of the compute and the communication. And then you have this is the compute, obviously, especially in machine learning, that becomes a very important resource. And then data, obviously, especially as we are entering a data. So now in terms of challenges, well, there are many challenges here, just to mention a few. How do you optimize space, frequency, time, resources? So this could be, how do you optimize your power allocation? How do you carry out your handover optimization? How do you mitigate interference, user cell association, traffic offloading, and so on and so forth? I mean, these are kind of old problem, but still very relevant nowadays, because now, again, the networks are becoming very, very complex, and which makes the problem even more difficult to solve. Okay, so the front and the backhaul. Then you have ultra reliable low latency communication, URLC, which on its own requires now a novel system design as opposed to the enhanced mobile broadband. And we will come back to it a little bit later to see what kind of utility of function we should use when I want to learn in a URLC setting as opposed to an eMBB setting. But here, the main takeaway here is, in fact, self-organization. And this is also related to the topic of self-organizing networks, or SON, which has been there for quite a while, but really became now even more important with the advent of more network complexity, more data available, and so on and so forth. So what is SON? I mean, at a high level here, I mean, the idea is to, of course, move away from the traditional way of manually configuring a network. This could be from configuring your base station configuring, for instance, whatever the tower. I mean, as you can see here, the guy is actually, I mean, he has to go physically and try to configure some parts of the RF chain here. But you could essentially use it for resource allocation, for again traffic offloading, mobility management, beamforming, and pretty much everywhere where you need actually to carry out a more intelligent decisions as opposed to pre-programming them in a static manner. Okay. So essentially, yeah, it's not a buzzword. It's actually very important. It is actually applied nowadays in a number of releases in 3GPP. And essentially, the interesting parallel here is that Sun and machine learning they have had their own winter. Okay, so it was very there's a hype in Sun, then it went down, then it went up again, and now obviously with beyond 5G and 6G, where machine learning plays a key role, Sun is actually again back on the research. So what is SON? I mean, the definition is very straightforward. It's the ability for a system to spontaneously arrange its component or elements in a purposeful, non-random manner, and their appropriate conditions, and without, of course, the help of an external entity. So think of it as a centralized entity, server, base station, roadside unit, right? And essentially, it includes three parts. So you have the self-optimization, self-healing, self-configuration. So self-optimization essentially is, again, how do you optimize the parameters or optimize them of a system as the network changes or as the state environment changes, right? Self-healing is in fact in case that there is a failure in the network or an outage. So how can the network heals on its own by, for instance, reconfiguring the transmit power, maybe turning on and off some base stations and so on and so forth. And of course, self-configuration is related to self-optimization. So as I said before, SON is not only an academic exercise. Essentially, you can go back in time and you can see that various network vendors, for example, here, Network Siemens Networks, has already been talking about SON for a while. And actually, if you look a little bit in detail, you could see that actually they're using vocabulary of reinforcement learning, right? So here it says, towards learning and cognitive network, learn from environment and create configuration automatically, right? Learn from former actions and adapt the decision accordingly, right? I mean, this is essentially for those who work in reinforcement learning will immediately resonate with this. Okay, so essentially sensing, learning, adapting. This is the control, the loop of even Joseph Mitola back in cognitive radio. So again, this is still an important aspect, although the slide is old, but we still are dealing with the same problem until today in 2020. And obviously we will see the link towards machine learning a bit later. Now moving forward, in 2017, we started to see actually a different trend in machine learning, again related to SON, obviously, because again, SON could include the entire wireless communication to some extent. We saw actually that some companies, and here is just one, this is Huawei, in fact, in Paris, looking more and more in terms of applications of machine learning in communication. Okay. So this is, I mean, these are just a few snapshots of some talks that were given in the 5G context. This is for self-driving vehicles and ability to make sure that the autonomous vehicle is carrying out its navigation in a safe manner. And then, of course, this is more towards our work here, where we saw this the big interest in terms of moving the intelligence from the cloud to the devices, right? So instead of carrying out machine learning in a centralized manner, why not doing it in a totally distributed manner, which opens up a whole new research agenda that we will cover also in this class, right? So again, yeah, pushing machine learning towards the edge. And of course, as you can see here, this is the French president. I mean, back in 2018, the machine learning took such an important place in the national agenda that even the president and organized a big 1 week long conference talking about what can machine learning do for humanity. So, needless to say, the importance of machine learning nowadays is really ubiquitous. Finally, maybe just a chart here to show a little bit the timeline of where we are today. So we are in 2020, but if you go back to 2010. Okay, this is where, I mean, the 4G era perhaps, and when we were talking about femtocells, picocells, SON, of course, early SON, we were using techniques such as Q learning, right? Then, of course, 2015, we started to talk more about maybe deep reinforcement learning for those who were really following a little bit the progress of DeepMind. And then Google came up with the idea of federated learning in 2016, and then 2017 saw the first basically kind of applications of it by Google again. And then you would see, of course, the wireless AI taking more and more role. This is in Mobile World Congress in 2017, and fast forward towards 2020, Edge AI is now a very important research for 6G. Right. So what's Edge AI? I mean, this is just a one slider, essentially to motivate a little bit what's behind it. So essentially what we are used to is the classical machine learning, right? Where we have devices, and this could be drones, could be vehicles, sensors, transmitting their data to a centralized server, right? And then, of course, you can carry out different machine learning tasks from training to inference, could be also reasoning, could be control, any type of task that you have in mind could be done in a centralized manner. So of course this violates privacy. So think of this as your, I don't know, the photo of your child. It could be your salary slip or any other confidential entity. For instance, in healthcare, right? This could be the patient's health record. This incurs high latency, right? And is bandwidth inefficient. So of course, it was obvious that we needed to move from decentralized case to the decentralized case here. So this is the one called federated machine learning, right? So here the idea essentially is, instead of transmitting the entire raw data from the device to the cloud, here I would just basically transmit a model, right, of this data that I have here towards the cloud, and then the cloud will basically essentially just carry out some model averaging on some other function, and then send you back the model, and then you could iterate this between the devices and the server until you obtain a reasonable model to essentially then use it to do some kind of local inference. So the benefits here are, again, very, very interesting, because here this is much more bandwidth efficient than the cloud-centric approach. You're still using the cloud. You're not getting rid of it, but you're just using it in a smarter manner, right? And very importantly, privacy. So here, by not transmitting the raw data, the learning mechanism is privacy preserving. Then if you want really to get rid of the cloud, this is the one here in the middle called Swarm AI or fully distributed AI. It comes under many, many names. Essentially, you want to, again, carry out the same task, meaning training a model, for instance, among many, many, many agents, and you could do it again, in a privacy preserving and scalable manner. And here you can see, I mean, so Google was the first one to popularize federated AI, and ever since that we saw a lot of new players, I mean, interested in the approach, from Nokia, Huawei, Samsung, Intel, Philips, Ericsson. I mean, pretty much all the ecosystem in mobile ICT is interested in this technique. Very good. So now let's move, I mean, towards game theory, right? So we want to cover a little bit what are the basics of game theory. So what's game theory essentially? Essentially, game theory is about modeling the interactions among multiple agents or players or decision makers. These come under various names, which are essentially coupled here. They could be coupled either via their utility function, or they could be coupled using the state dynamics, or a mixture thereof, right? And then we talk about being rational. So players here, rational means they need to take a decision that is benefit for their own utility. And here we can talk also about selfish behavior, where basically, again, the players want to optimize their own interest, disregarding the interest of other players. Okay. What are the components of a game? Well, there are three components. One is, as I said, is the notion of player or agent or decision maker, right? Then we have the notion of strategies or actions. So the strategy for a given player could be, for instance, to optimize its transmit power. It could be to basically, I don't know, allocate a given resource on a resource block, for instance. It could be to schedule a given user. It could be anything that you wanna consider here. Okay. Then of course there is this subtle difference between strategy and action, but I will come back to it later. Essentially, that strategies and actions are not always the same. The third component of any game is the outcome, because essentially here we are interested as of what is the outcome of this interaction or this coupling between these agents. This will lead us to this notion of equilibrium, and we want to understand, of course, some properties about this equilibrium. Okay. So again, I mean, I'm sure you have heard about game theory. If you haven't, I mean, most of you have probably watched Beautiful Mind, but essentially it was already, discussed in many movies. But me personally, I mean, Beautiful Mind is the best movie that talks about game theory. You have also used it for sure in your childhood games, so rock, paper, scissors, matching pennies, right? Essentially, yeah, you have either witnessed or used it in your everyday life. Well, because essentially it comes down to, again, taking decisions where you are actually not isolated in the world, but interacting with other agents or human beings around. So when do we use actually game theory, right? Because some people still do not understand why we need to even talk about games here. Where essentially, if you look at the single player, okay, this is maybe the optimization centric view here, right? You have either a static optimization problem to solve or a more dynamic optimization control. So this could be kind of optimal control or Markov decision process, right? These are under this category of single player. And then you have the multiple player. Again here, once you have multiple interacting, competing players, then that gives rise to the notion of a game. Okay, and here we can talk about again whether it's a static environment, right, which is referred to classical games, or dynamic environment, which is basically, as the name says here, dynamic. So here, here is a slide basically about the classical critiques of game theory, because it's good also to understand why people sometimes do not like game theory because they simply do not understand it. So here is one question. I don't want to spend my research career proving the existence of an inefficient Nash equilibrium. Well, it turns out, in fact, that the Nash equilibrium is not necessarily inefficient. Okay, the finding the Nash already provides guidelines for making the system efficient. So by that I mean, if you have multiple operators trying to say optimize their access to spectrum, right? You could actually already analyze what type of equilibrium one would get if we use, for instance, these principles of game theory before even deploying it, right? So it's a very interesting tool that allows you to analyze these interactions and then later on try to come up with an algorithm to approach this Nash. So, and again, game theory was already used during the Cold War, essentially to analyze what will be the final outcome if, for instance, a given country takes a given decision, for instance, to launch a, I don't know, nuclear bomb or maybe the troops, right? You would already beforehand know what type of outcome you would reach. And moreover, game theory goes Nash equilibrium. So we talk also about cooperative game theory, mechanism design, clustering, graph formation. So Nash is just one possible equilibrium. And yeah, this was an example basically of operators. So already mentioned it. Yeah, game theory still faces overhead and scalability issues, of course, but this again is valid for any optimization problem where we have a lot of agents to optimize over. You have a large dimensional space, which makes the problem untractable. These are again also, of course, valid also in the game theory front, but we will actually show that we can actually address this issue using tools from mean field game theory and statistical physics. All right, I mean, this is just one slide basically to keep in mind, very interesting because some people sometimes throw these questions, but now you know how to answer it. And the bottom line here really is that game theory is just a branch of mathematics. So just now, game theory again is a vast research area. So here in this course, we'll be just dealing with what we call the non-cooperative game theory, in which we will use the notion of strategic form to represent the game. So here under this, you could see that there are many solution concepts. So one of them is Nash equilibrium, correlated equilibrium, Nash bargaining, right? And then you have this other red umbrella here. This falls under the category of coalition games or cooperative games. And this is something we will not cover here, but this is just for information. And here again, you have different notions or concepts of equilibrium. We talk about core, we talk about Shapley value, and others, right? What we will be, of course, talking about is this Solution analysis. So here we will need to talk about the existence of equilibrium. Is it unique or there are many others? How good is it? How efficient, right? How does it approach the centralized case? For instance, if I have one omniscient agent that observes all the informations and come up with the best strategy for all the players, right? And then in terms of algorithms, here there's a lot of interesting approaches to solve game theory in general. So one of them is best response dynamics here, BRD, fictitious play, reinforcement learning, regret matching, consensus, right? And this is again just a selection of those algorithms, and we'll come back to them later on. So again, just keep in mind we are in this category here of non-cooperative games, okay? And we will actually go through over this Nash equilibrium, correlated equilibrium, coarse correlated equilibrium, and try to talk about their properties, okay? And then finally, the algorithmic part, because this is what makes, the difference between game theory and learning. Game theory, you would basically stop here, okay? You would just talk about whether it exists or not, is it unique or not, is it Pareto optimal or not. And then the question we are interested in, at least as an engineer, is what is the algorithm that allows me to approach or converge to Nash equilibrium or a neighborhood thereof, okay? Very good. And then, of course, there is beyond basically rationality, but this is something we'll not cover in this class. All right, so we are in the realm of non-cooperative game theory, okay? So essentially, let's go through this, and I already mentioned some of these aspects, but essentially what we're dealing with competing agents or players, right? And I will be using this actually interchangeably. So, when you hear a player or a decision maker or an agent, this is pretty much the same thing, right? Every player is selfish and cares only about maximizing his or her payoff or utility. And the utility here refers to the benefit that a player, okay, can obtain in a game. And we will see concrete examples of what we mean by utility, especially in wireless, okay? And then the equilibrium or the solution concept we are interested in essentially will be a point or a state in which no player, okay, has a benefit to change or update its preference or strategy. Okay. And just here a misconception, essentially that non-cooperation is not always competition, because as we will see is although sometimes you do not communicate directly with agents, you can actually implicitly coordinate, and we will see the corresponding notion of equilibrium dedicated to that, which will go beyond Nash equilibrium. So when we talk about Nash equilibrium, this is exactly when we do not actually collaborate nor coordinate, okay? So what kind of types of non-cooperative games we have? As you may expect, so there's a static case and a dynamic case. So the static game here is really when I have to make decision in one shot. This could be one time slot if you want. Then you have the dynamic game where the game will evolve over time. So you take a decision, you get your utility, and then depending on what the other agent took, then you can actually update again your strategy and so on and so forth. The game could be zero sum or non-zero sum. By zero sum means there's only one winner. Okay. By non-zero sum means, of course, all the agents essentially, still get an utility or benefit from the game. The notion of information is very important in learning, but game theory too is that actually we talk about complete versus incomplete information. So think of it as observing first the utility of the other agents. Number two, observing the action of the other agent. It could be also observing the state of the other agents, which of course are completely impractical, especially in a wireless setting. But this is where the difference comes between complete versus incomplete information. Finite versus infinite. Then you have different kind of representations here. Yeah, and actually that's it. Again, maybe a picture is worth 1,000 words here, but essentially, yeah. Over time, this is the interaction between the players, and this is one shot game because you observe the outcome immediately, or there could be a delay between what the players play as a strategy and what type of payoff they observe. Okay, all right. So I talked about representing a game in a strategic form. So what do we mean by that? Okay. So a game in strategic form will be defined by three elements. Okay, so first, a set of players, right? We need us to define what are the agents in the game. So this is here characterized by this set here, N. Then we have a set of action, of course. So every agent will have its own set of actions, and this is captured here by AK, right? K referring to the agent K. Then the payoff here will be a mapping between the set of actions to the real set of real here. So we will see what we mean by that. This could be, your channel rate, could be energy efficiency, power efficiency, anything else you want. And then, of course, the outcome will be to characterize this Nash equilibrium here. Okay. Right. All right. Action versus strategy. We can talk about it later on. All right. So let's take an example. And one of the most famous example is actually called prisoner dilemma. This is the one that is taught in every game theory course. So essentially what we have two suspects in a major crime held for interrogation by the police, but in two separate cells. Okay. And here are the statements or the hypotheses. If both criminals stay quiet, each will be convicted with a minor offense and will spend 1 year in prison. Okay. If one and only one of them thinks, means he lied, kind of talks to the police, confesses rather, he will be freed and used as a witness against the other, who will spend 4 years in prison. Now, if both of them think, each will only get 3 years. So compare here. If they kind of both think, they will get 3 years. Otherwise, they will get 4 years. And if they both stay quiet, they will just get 1 year. So essentially, this will be probably the kind of the selfish approach here to find our Nash. Okay. So what are the components here? Well, it's very easy. We talk about the players, which are the prisoners here. The strategies are either to confess or not to confess to the police. And the solution is actually what is the solution of the game. So let us first write this down as a strategic form. Okay. Here is what we get, right? So this is gonna be basically, so P1 not confess, P1 confess. This corresponds to the strategies of the, say, player 1, right, or criminal 1. P2 non-confess and confess refer to, of course, to accordingly to the second criminal. So he can either confess or not confess. So now let's see what we get, right? So now if the first criminal doesn't confess, we want to look for the Nash. So what would be the best strategy in response to that? So now if I don't confess, right, and the second criminal doesn't confess, I get -1, right? If I don't confess and he confesses, then I get 0, right? So here, this is one thing. Now vice versa. If I confess and the player 2 doesn't confess, right, I get 0, he gets -4. If I confess and he confesses too, we both get -3. Right? So again, if I choose, let's call them player 1. If player 1 chooses non-confess, the best strategy or best response of player 2 will be to confess, right? Because here you get 0, right? And here you get -1. So 0 is larger than -1, therefore I need to confess. Likewise, if player 1 chooses confess, what is the best strategy? Of course, it's going to be to confess because, -3 is larger than -4, right? So this is essentially the idea. Maybe a remark here is that actually for the player 2, confessing is the dominant strategy. Because here, if I take player 2, if he takes confess, so the other guy will get actually -4, -3. So this is a better approach here. If he chooses here, again, whereas if he chooses here not confess, basically, yeah, it's -1, -1, and 0, -4. So he would rather be here. Therefore, confessing is a better strategy in all cases compared to non-confess. All right. And this is the Nash equilibrium, right, of the game. Why again? Let's see why. It's because if player 1 confesses, the best strategy for P2 actually is to confess, and he gets -3 as an outcome. And both players get -3, right? This is essentially the idea. All right. So what is a Nash equilibrium? A Nash equilibrium is a strategy profile S star with the property that no player I can do better by choosing a strategy different from the optimal one, right? Given every other player J different than I. Okay, this is in words, right? So essentially, that if I write down for player I with payoff function ui, the utility that he would get, right, if he plays the optimal Nash, I shouldn't use optimal here, the Nash equilibrium S star, right, given that the other players here, minus I represent the other player, S star, this will be larger, greater than, well, if this guy here chooses any other SI which is different than SI star. Okay, so hopefully this is very clear. I mean, it's a very easy definition. Okay, so we say that Nash is actually robust to unilateral deviation. All right. In other words, it just means that no player will have an incentive or motivation to change the strategy given a fixed strategy vector by all the opponents, meaning these other minus A. Because of course, if I change my strategy, I know I will get a worse one, right? So why should I do that? And vice versa, obviously, because this I applies to all the players. Okay, so all the player will need to have this inequality satisfied. Okay, and this is how we will find the Nash equilibrium. So some important questions we always need to ask is, first, does the Nash equilibrium always exist? The other question is it efficient, right? So in order to characterize that, there are many measures of efficiency. What one of them is Pareto Optimality, essentially which says that a payoff vector x, right, is Pareto optimal if there is no other payoff vector y such that y will be larger than x, with of course at least one straight quality for an element yi. Okay. So we will. I mean, you see, it's not always the case that we have Pareto optimal vector, but it could happen in certain cases, and we will see an example of that. In such a case, we talk about Pareto optimal strategy. So as I said before, in non-cooperative game theory, we'll be talking about pure strategies and mixed strategies. So let's focus first on pure strategies. So we said that SK denotes the action taken by player K, right? And let S be the vector S1 until SK be a joint action or action profile. Then with the slight abuse of notation, we will always be writing S equals to SK, S minus K, where S minus K is essentially referring to the other agents other than K. Okay, so we can write it down here, S1 until SK minus 1, skip SK, and then it's SK plus 1 until SK. Okay, this is just for facilitating the notation, all right? And then when the action adopted by the players will be essentially S1 SK, then you can write down the utility of the player or the payoff, which is simply UK SK S minus K. Okay, this is just facilitate again the notation for what for what comes next. And then we say that actually for all K, any element SK is going to be a pure strategy of player. All right. So let's take an example. So here we already talked about the prisoner's dilemma here, and in the case where the both criminals actually do not confess, they will get -1, right? Which is actually corresponding to a Pareto optimal, because if any of them decides to deviate from that, and of course the other takes that into account, then he will be getting a lower utility. Whereas if you look at for the Nash equilibrium, this is going to be again corresponding to the both confessing. To summarize, if we look for the Nash equilibrium and we decide to follow the sacrificial approach, it is better actually that they do not confess, because if they do confess, they will get a worse outcome if they don't do so. All right. So here is an example essentially where you can compare both. The difference between a Nash equilibrium and a Pareto optimum. All right. But again, as I said before, this will not be always the case. Sometimes we cannot find the Pareto optimal, whereas we can find the Nash equilibrium. Sometimes we can actually not even find the Nash equilibrium in pure strategies, and we will need to look at different notion of mixed strategies for that. All right. Now, pure versus mixed strategies. So far, we assume that the players make deterministic choices, and that's why we called it pure strategy, by the way. Okay, so we said that strategies are pure if a player I selects in a deterministic manner, which means with probability one strategy out of its strategy set, right? Now, if we want to, of course, extend that, and it's kind of very obvious what we will do, is essentially to introduce a probability distribution over the actions that the player I can take, and this is essentially what we will be referring to as a mixed strategy. So again, so players can select probability distribution over the set of strategies, okay, which we will be calling a mixed. And this is essentially one of the pioneering results of the famous John Nash in 1950, that every finite strategic form and player game has a mixed strategy Nash equilibrium. This is a fundamental result, essentially, which constituted his thesis, essentially that in the pure strategy case, it is not always so that that Nash equilibrium exists. However, in the mixed strategy case, there will always be an equilibrium. And this is fundamentally, essentially, in the game theory field. All right. But essentially here you can see what we talked about a bit, right? The strategic form, right? If I have n players, which are of course non-cooperative, right? And I talk about basically a mixed strategy as opposed to pure strategy. So we already have a theorem that tells us that yes, it will exist, right? At least one, at least. It doesn't tell us how many, and it doesn't tell us how to approach or converge to those equilibria. All right. Okay, so again, some notations here just to write down what we mean by mixed Nash equilibrium. So here again, we will define sigma r here as the probability, or PMF, the probability mass function over set strategies SI, okay, which are the set of actions or strategies. I mean, these are interchangeable for now. Now, unlike pure strategies, when working with mixed strategies, every player I will again maximize now its expected payoff, right? So why expected payoff? Because now I have actually a probability distribution function, or PMF, over the set of strategies, right? And to write it down essentially is very easy. This is a utility I of player I. Sigma here essentially refers to the probability distribution that he has, right? And it is a sum over S, right? Of remember, S actually is a set of actions or strategies, right? This is the utility of player I when he chooses strategy S, right? But of course there are many, and there's also the product of the basically the strategies or probability distribution function of all the players, right? So this includes actually all the players J until I. So here I have maybe I players, right? And then I need to take into account also the the priority distribution function of the strategies that they have actually selected. Okay, so in compact form, this is how we would write the expected payoff. Now, to write down the mixed strategies in the Nash equilibrium, this is essentially following the same as in the pure strategy. Remember, in the pure strategy, this equals to 1, so we get rid of it. We just get, you know, the definition of a pure strategy. Here, because we have essentially introduced this probability distribution over the strategies, the notation remains the same. Essentially, that if sigma r is the Nash is a mixed strategy, or mixed Nash equilibrium, then the utility of I, right, when he chooses this strategy, given that the other player chooses this strategy here, will always be larger than if the player I deviates from that strategy. Okay, so this is essentially the only difference, right? When we move from pure to mixed strategy, is we introduce a probability over a set of strategies or actions that the players will adopt. Okay. Now, so this is pretty much the same thing here. Is that essentially that if you want to write this down, right? So we would say that a mixed strategy profile is a Nash equilibrium for all players K and for all the S prime K. The following inequality holds. So essentially, what we're writing here is this: the expectation over all the probability distribution of the strategies of player K when he chooses SK and the other player chooses S minus K, remember minus K refers to all the other agents, is larger than if he chooses a different strategy than the Nash equilibrium, right? Now, if you want to develop this further, essentially it just comes down to this, right? This is the sum of the strategies S. You multiply, of course, here, this is the product of the probabilities of all the strategies taken by all the other players. This is the utility here, larger than the same, where you just remove basically minus K. Okay, so these are basically equivalent. All right. Now, if in the pure strategy, I will just take this to 1, right? So this will actually, collapse, and I'm back to the same. Basically, there is no expectation here. Okay. If you have mixed strategy, then you introduce expectation over the strategies of the player. Pretty straightforward. Okay. Very good. So again, let us now see how we would find a mixed strategy now in some examples. And this is one famous example again, which is referred to the battle of sexes here. Here you have a man and a woman, maybe husband and wife, where, for example, the man wants to go to watch football, and the wife wants to go watch opera. So, they're trying to basically find a suitable mixed strategy, because in the case of pure strategies, there's no equilibrium, satisfactory equilibrium for both, right? So let's see. So now if the husband so the husband is here, right? The wife is here. If the husband picks opera, okay, he wants to go to opera with probability P. Remember, now we are in a mixed strategy case, so we need to introduce probabilities over our actions, right? So with probability P, he picks opera. Then the wife will pick opera with probability Q, all right? So if we do that, right? So remember here, husband takes opera, right? Then the wife will actually take opera with probability Q. If you want to calculate now the expected payoff for the husband picking up the opera, well, what he's gonna get? He's gonna get 2, right? This is the utility 2 multiplied by the probability that the wife chose opera. And what is that? That's Q. Remember, this is P 1 minus P, Q 1 minus Q. So it's going to be 2 multiplied by Q, right? Now, what's the expected payoff for the husband picking up football? Now I come here, remember. So it's going to be, the utility you will get is 3, remember? 3, right, from here. And remember, the wife was taking opera with probability Q, so therefore she will take football with probability 1 minus Q. So 1 minus Q multiplied by 3. This is essentially how we calculate this payoff. So very, very easy, right? Now we said that at a mixed Nash equilibrium, the expected payoff as a strategy is equal to that. We need to make them equal, right, on the expected sense, right? So if we do that, if we make these two expectations equal, right, then 2Q equals 3, 1 minus Q, or 2Q equals 3 minus 3Q, then we can find Q. Like Q will be equal here to 3 out of 5. And then we can calculate the mixed Nash equilibrium. So the husband will take 2 out of 5, 3 out of 5, and the wife will take, the mixed Nash equilibrium is 3, 5, 2 out of 5. So very easy example. You can go through it again. Again, here you just calculate the expected payoff for the husband, right? And equal this because the expectation, right? Find Q. Okay, then you would find what is the probability that the husband should take in order to make sure that the expected payoffs are equal, right? And once you have Q, you find the other one. Same for the wife, right? You can redo the same calculation for the wife, right? And yes, expected payoff are 6/5 and 6/6 for the husband and wife, right? So if Q equals 3, 5, right, you could find 6 out of 5, and for the other one, it's going to be 6 out of 5. Now, of course, we can spend some time on a number of examples. So maybe I will leave this to you to actually do at home. So essentially, to see when we can find pure strategies and mixed strategies. So first of all, try to find a pure strategy, and then if you don't find it, then it doesn't exist, right? And then for that, you would need to introduce now a mixed strategy, and you can do the same thing as we did before with the husband and wife. So here is an example, for instance, when there is no pure strategy. Why? Let's see. So now I have this is a tennis game, right? Tennis match between Serena and Venus, right? For those familiar with tennis, they would know who is Serena and Venus Williams. And now this, for instance, Venus here can hit the left or right, left, right, and then likewise for her sister. So we can see here, if we want to look for pure strategy, let's see. If Venus takes left, what would be the best strategy for Serena? Will be to take left, right? Now, on the other hand, if Serena picks left, what's the best strategy for Venus? It's not going to be left, it's going to be right. Therefore, see, we cannot find the pure strategy in this case. However, there will be a mixed strategy. So let's find it, right? So let's apply what we used in the previous slide. So I write down the expectation for Venus when she chooses left, right? It is gonna be equal to 50. This is the utility she gets. because she chooses that with probability P, remember? She chooses left with probability P, right with probability 1 minus P. Therefore, it's going to be 50 multiplied by P, by Q, right? Because Serena will take Q, right? Or it's going to be plus 80 multiplied by probability that Serena will take, which is 1 minus Q. Likewise, you do it for the right? So it's going to be 90 multiplied by Q plus 20 multiplied by 1 minus Q. And again, you equate both equations and find out that Q equals 0.6. All right? Then you do the same thing for Serena now, right? So you come here, right? Now we are not dealing here, we are dealing with Serena. So you can also take left and right and try to find the corresponding expectations, equate them, and find the corresponding P, okay? And then we find out actually that the Nash equilibrium is going to be 0.7, 0.3, 0.6, 0.4, okay? So hopefully this is clear. And if it is not clear, we can also do it at home, or you can also raise it during the tutorial Q&A session, all right? Very good. Okay, so now, as I said before, regarding the existence of a Nash equilibrium, we said that in previous strategies, Nash equilibrium might not always exist. And here is again yet another example. Okay, so here, if I want to quickly look for the Nash equilibrium, and I think you should by now try to develop in a fast way how to find it. Okay, so I look here. Okay, if I take T, the best strategy here will be 1. Okay, so this is a good candidate. Okay, let's see. If player 2 takes H, okay, my best response will not be here, will be here. See, so I cannot actually find a Nash equilibrium, and you can try to verify it also during any other combination. Okay, and remember, what is the definition of a Nash equilibrium? Okay, this is always important to keep in mind. Okay, so a Nash equilibrium might not be unique. This is drive home message in the pure strategy case. Okay, and we will see it actually in many other examples. There is this example of battle of sex games. I mean, I'm not gonna go through this. I mean, yeah, we already covered a little bit with the husband and wife in the ballet, opera, football game. Sometimes you can find actually 2 equilibria, but you don't know which one it is, right? And then, of course, as we said before, the mixed strategy, thankfully, always exists. Why? Thanks to the theorem of John Nash. All right? Very good. So, in addition, John Nash actually in 1950 gave us, I mean, in his famous paper, which is called Equilibrium Points in N-Person Games, right? Gave us actually the existence, right? As I mentioned before, that every finite strategic form game has a mixed strategy equilibrium, right? And then there are other characteristics which are very important when it comes down to proving uniqueness. Okay, one of them is that actually the best response is a compact, convex, non-empty subset of the of an Euclidean space. The best response is non-empty for all the strategy profile. It's a convex, and then it's a closed graph. Right? These are essentially needed when you want to now prove that, I mean, the uniqueness of a Nash. But of course, these are sufficient conditions, not necessary. All right. Now, for the more difficult case of uniqueness, things get, again, more difficult, right? And there's a reason for that. So typically, in order to prove the uniqueness, you need to ensure a number of assumptions, as in every proof of uniqueness, typically that's the case. So Joe Rosen actually in 1965 came up with actually the existence and uniqueness of equilibria for concave N-person games. So first of all, here's a strong assumption here that we need to consider concave N-person games, which actually reflects in the utility function. So the utility function has to be jointly concave across all the players. But there are also other assumptions that one can actually leverage. One of them is monotonicity, right? One of them is also scalability. And actually, even in wireless communication, if you're people familiar with Roy Yates from Rutgers University, he also tried to look at a bit what does this mean actually in wireless setting, right? So if this, consider this game here in strategic form of player K, this is a set of strategies, this is a set of utilities that player K will get, and you make the assumption that the best response function are standard, meaning that they are monotonic and scalable, therefore here the game has a unique Nash equilibrium. This is a very nice theorem that one can readily use to prove actually the uniqueness, not the existence, of course the existence we have it, but the uniqueness of the Nash. Obviously, in real life, I mean, application, we don't necessarily have a concave problem. Therefore, this will not be applicable. But in certain cases, for instance, in power allocation games, water filling games, this actually property does hold, which allows us to actually have a nice result in terms of uniqueness. All right, but just a recap here, as I think we're getting already towards the end of this first part on basics of non-cooperative game theory. So we already saw that actually Nash equilibrium will be a predictable outcome of the game, right? We can analyze it beforehand, before talking about even an algorithm. We can actually analyze its property, right? One of them is that it is stable to unilateral deviation, and this is given to us by the definition itself that we saw before. Nash equilibrium might be stable to joint deviation. For instance, if you have k players and maybe, I don't know, 10% of the players deviate from that Nash equilibrium, you might still be stable, actually, right? It is also it was shown that Nash equilibrium might not always exist, right? Especially in the pure strategy case, right? But Nash equilibrium, I mean, Nash himself gave us the solution in the case of mixed strategy, right? So you should already be now familiar with the difference between pure strategies and mixed strategies, right? And what's the difference? Not only that, can I talk about uniqueness? Can I talk about existence, right? And of course, the last point is Nash equilibrium might not always be unique. That said, Nash equilibrium, again, as I said before in the introduction, is just one type of equilibrium. There are many others. So one of them is the generalized Nash equilibrium, satisfaction equilibrium, and we will have an example on this. Then there is this family of correlated equilibrium, which actually we will show that it is much more powerful than Nash equilibrium. So one is called correlated equilibrium, and one is called coarse correlated equilibrium. This will be part of next week's lecture. Essentially here, as the name suggests here, we will be exploring the fact that although the players do not communicate explicitly, they could still improve upon their utility or performance when they leverage correlation between the strategies. Okay, so again, this will be a very important aspect to go beyond Nash, because Nash does not allow you to exploit correlation. Okay, why? Is because if you go back to the definition, you would see that there's a product over the probability Nash function, right, of the strategies, and that means that actually they are completely independent. There is no correlation, right? Now we want to exploit this joint distribution, if you want, between these strategies, and that will give rise to this notion of correlated equilibrium that will be covered again in the next week. Okay. Here, finally, just a few slides here to talk about whether, again, the concept of Nash is really useful or not. But I think you already got the point, right? I mean, this is a very important tool to analyze interactions between competing players. It could be, by the way, base stations, which could be devices, vehicles, drones, and so on and so forth, right? Now, if I really want to maybe now try to add more constraints, for instance, here in a minimum quality of service game, maybe one radio device or one operator wants to, for instance, optimize its resources, and he wants to add a constraint. Maybe, I don't know, that my minimum target rate is above a given threshold. How do you take that into account in a game? And is it still Nash equilibrium, or are we talking about a new family of equilibria, right? In this case, yeah, as I will just show in the next slide, that the concept of Nash may actually fail to capture this quality of service requirements. Okay? So here it is, right? It's called game with constrained set of action, right? Because that's what I want to do. I want to make sure maybe that, if my utility is not above a given threshold, I will not even transmit, right? How do you encode that in a game? So let's consider this game here, G. Okay, I mean, this you should also be now very familiar with this notation here, right? It's the same notation that we'll be using throughout this course. So the set of players, set of the strategies here, S, and the utility K, okay? UK, sorry. And then now we assume that the set of actions of players is constrained depending on the action of all the other players. So now to write it down, we can write there is a mapping or correspondence between the set of minus K, so all the other agents, right? And then basically the what type of available action does the player have, right? And then you encode it here. See here? You add it as a encoding, right, in the game, so which gives rise to now G prime, right? And then you can write it down now here. For instance, this is a minimum transmit power location problem with rate constraint. This is a very, kind of a total example in wireless communication, right? You have a multiple access channel with the players, transmitters, sensors, whatever you have. Maximize the transmit rate, and they only transmit when a minimum transmission rate is guaranteed. So we can actually model it, and this correspondency here between this the set here is actually encoded by simply saying that the utility of player K is larger than this gamma K threshold, right? That's basically it, right? So now if you want to show visually what we get, this is basically the transmission rate. This is in the case of two players. Transmission rate of transmitter 2, transmission rate of transmitter 1. Remember, I'm in the uplink multiple access channel, okay? Then now if I want to plot the achievable region, this is what I get, right? This is all the red points here. I get this is achievable region, right? From time sharing to basically transmitting at the same time. And then I have the minimum rate for transmitter 1, right? Given basically here. Transmission rate of the second agent. So then I'm already here, right? Then if I want to look for Nash equilibria, look what do I get? You see the Nash equilibria will favor transmission rate of the first player, you see, but the other one will actually be lower. Why? It's because we do not impose or encode these rate constraints, right? Now I want to go beyond Nash, so now I am in the context of satisfaction equilibria. Essentially, among the achievable region, I want to ensure that my rate is larger than a given threshold gamma k, which is given here, by the way, by 0.6, 1.2. 0.6, 1.2. All right. So this is what we get, right? And then here, of course, then you have different equilibria. This is generalized Nash here, and this is the efficient satisfaction equilibria. Here we are really focusing on the notion of satisfaction equilibria, which is, by the way, better than Nash for both players. Of course, this is the case, right? Again, this is really just an example to motivate a little bit why we need sometimes to go beyond Nash, because Nash does not, again, encode constraints in terms of the set of actions or even the set of utilities.
So with this, we reached the end of the first lecture. So now the next step is actually for you to attend a tutorial, which will be given by Sumudu. I think the link will be shared with you very soon. And then after that, the following week, we will be basically moving on to the reinforcement learning part, which will actually build on the game theory part. We will see the link between, characterizing equilibria, right, and exploring their uniqueness, existence, towards now, finding algorithms that will allow you to approach or converge to those equilibria, and that's the goal of this second part dedicated to reinforcement learning. Okay, so talk to you very soon. Bye-bye.